Hey everyone, in this video we're going to go over section 2.2, the limit of a function. In this section we're really just trying to strengthen our understanding of what a limit is and discuss what it means for a limit to tend towards positive or negative infinity. So let's start by trying to further develop our intuitive understanding of what a limit is. For this example, let's talk about the function f of x is equal to x squared minus x plus 2. And in particular, let's talk about what happens as we take the limit as x goes off to 2 of this function of x squared minus x plus 2. So remember what this notation means. This means as we let the values of x get very, very close to 2, what is happening to the y values of this function? Well, I'm going to show you a table at first, and we'll look at a graph. But for now, notice how as x gets closer and closer to 2, the y values, f of x, they are getting closer and closer to 4. An important thing about limits, and we'll discuss this later in this section, is that they have to agree. That means that as we increase in value to 2, the function limits towards 4, and as we decrease the value of x towards 2, the value of the function also tends towards 4. You can think of it as we look in a very narrow window around 2, what are the y values doing? So let's look at a graph to help illustrate this. So here we are, looking at Desmos again. We have the graph of the parabola, x squared minus x plus 2, and this is the same table of values that I had. Notice how as x is getting closer to 2, y is getting closer to 4. Similarly, as x is getting closer to 2, y is still getting closer to 4. Let's animate this real quick, because calculus is dynamic. Look at what we have here. We've got this narrow window around 2, and as our x values, these are our x values, or you can look up here for x values, as our x values are getting closer to 2, our y values keep on approaching 4. Now, the thing is, it doesn't matter what happens when x is equal to 2. All we care about is what happens as x is close to 2. I'll say that again. It does not actually matter what happens when x is equal to 2. The only thing that matters is this overall pattern in the y values. And then it bounced back, started over. As the x values are getting closer and closer to 2, the y values are tending towards 4. So that's why, going back to this notation that we use, we say the limit as x tend towards 2 of the function x squared minus x plus 2 is equal to 4. So now the book goes on to give us what they call the intuitive definition of a limit. And I copied this out of our book, but I want to kind of give some background, give some context to what they're saying. So the definition out of our book, and I might as well share this with you, save you guys from having to read my handwriting. Suppose f of x is defined when x is near a. That's worthy of a circle. In fact, the word near by itself is worthy of its own circle. That's what I was saying. In this example, it didn't matter what happened when x was equal to 2. We only care what happens when x is near a number. This means f is defined on some open interval that contains a except for possibly a itself. So that means, right here, for this function f, we have two possibilities. The domain of f can either contain a, or it's possible that the domain of f looks something using interval notation, where we've got a number over here, and some different number over there. So we can either have a be in the domain of f, or a does not necessarily have to be in the domain of f. And then we write the limit as x goes to a of that function is equal to L. That's what we have over here. The limit as x goes to 2 of that function is equal to 4. We're just using an a for a 2 and an L for a 4. And we say the limit of a function as x approaches a is equal to L. Or, and I see this notation a little bit more in once you get out of calculus classes, that f of x tends towards L as x tends towards a. Approaches, tends, there's a lot of different ways to convey this idea. Another way of thinking it is that f of x can become as arbitrarily close to L as we like. Putting a box around that so I remember to edit it. So limits are talking about y values, but we are looking through a specific window. The reason why we can say this is because we can come up with some value of x that will get us as close to 4 as we like. What do I mean by that? That means if, let's say we wanted to come up with some x value for when f of x is 3.9999999. I've got 8 nines right there. We could come up with some x value. If we wanted to come up with another x value, well, now we've got, what, 12 nines? We could come up with an x value that would give us this number. And similarly, I can tack on another 4 nines. We could come up with an x value that gives us this number. As close as we want this number to be to 4, and I could have gone through and put zeros here. As close as we want this number to be to 4, there's always some x value that'll get us there. But it doesn't matter if the value we care about is in the domain of the function or not. I'll give you some examples to help illustrate this. So in order to best do this, I think some pictures are in order. Oh, come on, pen. So, once again, you guys can see my lecture notes, and I've got them nice and typed up here, so let's just take a look at what I have here. Now, instead of me telling you to pretend like all 3 of these look the same, all 3 of these look the same. You can tell we have a really high production. We got a lot of money to produce this video, I'll say that. So, we have this same function f of x. It's almost identical in all 3 of these graphs. But in all 3 of these graphs, we would say that the limit of f of x as x approaches a is equal to L. That's saying that as our x values, and this is our x-axis and this is our y-axis, as our values of x get really, really close to a, our values of y get really close to L. And this is a continuous function. Right here, we would have f of a being equal to L. We also have the limit, and I'll write that above, the limit as x approaches a of f of x is equal to L. That 4 is from the previous example. In this graph, we have the same thing. As the values of x get closer and closer to a, the values of y get closer and closer to L. It doesn't matter that the function isn't defined at a. There is no f of a on this graph. As we're letting those values of x get closer and closer to a, the values of y are getting closer and closer to L. So in this one, f of a does not exist. But the limit as x approaches a of f of x is equal to L. Because once again, we're talking about patterns. We're talking about trends. As these values get closer and closer to A, these values get closer and closer to L. This one's kind of tricky. Now, if you look, and I'm going to give this some, we will call that B. This Y value is B. If you look in this third graph, f of x, or f of A, is equal to B. We have a Y value associated with this x value. But if we take a look at the limit as x approaches A of f of x, as these x values get closer and closer to A, the Y values get closer and closer to L. Doesn't matter that the function isn't, it doesn't matter that the value of y, the value of f of x, jumps at A. We're talking about the overall pattern, the overall trend. So this limit is also equal to L. This hopefully illustrates the point that it doesn't matter what the function does at the point. The only thing that matters is what the pattern of the function, the trend in the function is, as our values of x approach some number. And so that's why with functions like x minus 1 over x squared minus 1, and we'll get away from you guys just reading my lecture notes in a second. I just don't want to copy tables down for you. So this function, this f of x, is equal to x minus 1 over x squared minus 1. So this function isn't defined when x is equal to 1. X cannot be equal to 1 in this function. But we can ask, what is the trend in this function? What does this function look like? Or what do the values of y do when x tends towards 1? So we start far enough away to kind of get a running start at it, if you will. And we plug in 0.5 and we get 2/3, and we plug in 1.5 and we get 0.4. Plug in 0.9, 1.1, and we start to observe a pattern as these x values get closer and closer to 1. At no point can we plug 1 into this function. It's out of the domain of that function. This function is not defined when x is equal to 1, but we can continue this pattern. And this pattern in the numbers, and the first row doesn't really tell us anything. The second row, okay, we're starting to get closer, and I go, okay, I'm starting to notice a pattern. As this value tends towards 1, this value tends towards 0.5, or this value tends towards 1/2. Similarly, this value is tending towards 1. As x is getting closer to 1, the y values are getting closer and closer to 1/2. And that's why we say the limit of that function. We say the limit as x approaches 1 of x minus 1 divided by x squared minus 1 is equal to 1/2. Because as the values of x get really close to 1 from both sides, the values in y are approaching 1/2. This next one should drive it home. Now we have a piecewise defined function, and we'll take limits of piecewise defined functions. It behaves like a normal function. We'll work some examples of this later on. But if we just wanted to talk about the limit as x approaches 1 of x minus 1 over x squared minus 1, or 2 if x is different than 1, or if x is equal to 1. This piecewise defined function has a jump discontinuity, or a removable discontinuity. It's got a dot beneath the graph, or above the graph. But it doesn't matter that now this function, this piecewise defined function, is now defined when x is equal to 1. What we're doing is we're still talking about the overall trend in y values. It's like in this example, we were tending towards this value y, and we were tending towards this value y, but at the point A, our y suddenly jumped. that didn't matter because limits are talking about overall patterns. One jump isn't going to change the overall pattern. So as our x values are getting closer to a, our y values were approaching L. Over here, same thing happens. As our x values are getting closer and closer to 1, our y values are getting closer to 1/2. It doesn't matter that when x is equal to 1, y is equal to 2. That overall pattern says that as x is getting closer to 1, y is getting closer to 1/2. So at this point, it seems like if we wanted to, let's say, discuss the limit as t goes off to 0 of the square root of t squared plus 9 minus 3, all divided by t squared. Cool. So it seems like we only care about numbers that are really close to 0, which is true. What's stopping you guys from just picking an incredibly small number? What if we let t be equal to 0? That's 12 zeros and a 1. Well, this example is more a warning about computers than the limit of this function. I'll say it again, and this will be the last time I show you guys a chart I am too lazy to copy down. We're letting t get closer and closer and closer to 0. Note, we're always going to square t. Doesn't matter what value t is, we're going to square it. That's why I can say plus or minus 1, plus or minus 0.5, plus or minus 0.1, plus or minus 0.05, because if let's talk about 1, that's easy. 1 squared is going to be equal to 1, but negative 1 squared is also going to be equal to 1. So positive 1 and negative 1 are going to give us the same value from this function. Same with positive and negative 1/2, and positive and negative 1/10, and positive and negative 1/100th. So that's why we're saying plus or minus over here. And if you look, a pattern emerges. And it does. It goes to about 0.1667. That's a fraction. I can't remember what it is off the top of my head. I think that's a sixth. So as we let our values of t get closer and closer to 0, our values of y approached 0.167. We'll say that. Approximately 0.167. Which is fine. But I want to talk to you guys about computer round-off errors and what happens if you just try to plug this incredibly small number into this function on your calculator. At some point, when you square this number, it's going to get even smaller. And the computer's not going to necessarily recognize that number. It's going to be so small in the context of the numbers that it's working with that it's going to round it down to 0. So if you try and use a computer to evaluate this problem, eventually it will say this function is equal to 0. Well, the only way for this function to ever equal 0 is if the numerator equals 0. And since we can never plug t equal to 0 into the numerator, this numerator can never equal 0. Let me show you what I mean. Like I said, this is really going to be a discussion about round-off error and being careful with your calculator. So I've got this same function plugged in over here. This is our t, this is our f of t, and these are the values that we were getting out of our table. A couple more decimal points because I'm using Excel instead of what was provided in the book. And in the example, we went to 0.01. And these values match what we have in the table. And if we go 0.001, an extra 0, we can get another value. But if we continue to make this number smaller and smaller and smaller, oh, that's not what I wanted. We want u to be equal to the number above it divided by 10. And let's drag that down a couple times. There we go. So it switched over to scientific notation. And we're continuing the pattern. But notice how small this is. This is 5 zeros in front of that 1. 6 zeros in front of the 1. 7 zeros in front of the 1. And suddenly it jumped from 1.665, and if you notice, that's starting to look kind of weird. It's like the pattern broke right here. Suddenly, my laptop is approximating everything as 0. This is because the value of this number over here squared is so small that the computer is having difficulties recognizing it. This is it's kind of a word of caution about just trying to plug an incredibly small number into a function. If you plug in a number small enough, your computer might have difficulties recognizing it. So now I've got two examples for you. We're going to quickly switch back over to my laptop. Just for you guys following along, this is going to be example 4. And example 5. So if you go on Desmos and if you want to mess with these graphs, the graph for this one is going to be 251, 2.2 EG4, and 251, 2.2 EG5. A little note about these examples. If you go through our book, and hopefully you guys are going through our book, sorry, I had to make sure that the camera was recording. If you guys are going along in the book numbers all of its examples. I don't necessarily always do the same examples that the book does. Sometimes there's points I want to stress that the book necessarily doesn't. So I don't know if this is example 4 and example 5 in our book, but it is definitely example 4 and example 5 of this lecture, and the graphs on Desmos are called example 4 and example 5. The first one that we talked about, the one for this function, x squared minus x plus 2, that's intro. That's going to be 251, 2.2 intro. But these are the two graphs. Let me pull them up on my computer. So for this example, example 4, we're going to be talking about f of x is equal to the sine of x divided by x. And though it's not written out front, what we actually care about is the limit of this function as x tends towards 0. So if you look, this function isn't defined when x is equal to 0. If we plug 0 into this function, we'd get 0 divided by 0. Later we'll call that an indeterminate form, and we'll use some tools to deal with it. But for now, just know that we can't plug 0 into this function. We can't divide by 0. But what we care about is we care about the overall trend. And as x is, and we're going to bounce way back to negative 0.5. Let's do negative 0.1 to 0.1 and let that play. So as our values of x are getting really close to 0 from the left, our values of y are getting closer and closer and closer to 1. And as we're going to get closer and closer to 0 from the right, our values of y are going to get closer and closer to 1. So once again, it does not matter that this function isn't defined at 0. What matters is that the y values slow down. The y values tend towards a specific value. Because sine's a trigonometric function. It oscillates forever. If we were to scroll out, and we're getting smaller because we're dividing by a value, but you can see we're going to oscillate forever. But the numbers slow down and tend towards a specific value. Once again, it doesn't matter that this function isn't defined when x is equal to 0. We can snap this thing over And at 0, it would say undefined if it had a point to put on the chart. But now let's take a look at a different function. We're going to look at the same trigonometric function. We're just going to change its argument. We want this one. Take a look at this. We have the sign of pi divided by x. And as we let the value of x change, look at what happens. We're going to bounce from -2. As we get closer and closer to 0, the value of g of x is going to oscillate infinitely between -1 and +1. This function is never going to slow down. This function isn't going to settle down and tend towards one specific value. In fact, I bet you that if we go like this, let's plug in some values close to 0 and see what happens. We can plug in 0.5, 0.4, 0.4, 0.3, 0.2, 0.1, 0.01, 0.001. Once again, Desmos is rounding for us, which is very nice of it. This is a very strong graphing program, but isn't necessarily the most useful for algebra sometimes. The point I'm trying to drive home is that this function is going to oscillate infinitely fast near when x is equal to 0. Since this function is never going to slow down, it's never going to tend towards one specific number. This limit does not exist. This is the first example, I believe, of a limit that does not exist. Like I said, those y values never tend towards one specific value. The closer we get to 0, the faster the y values change. So this limit has no value. You would say the limit does not exist. We can use DNE. I'm not too terribly picky on whether you abbreviate or not. But yeah, this is the first example when a limit does not exist. Cool, so limits might not exist. And so, up until this point, I've been saying that we have to approach the value, and I'll write the limit as x approaches a of some function. That x has to tend towards a in both directions. That's for a plain old limit. But what we can do is we can talk about one-sided limits. A one-sided limit. So let's talk about the Heaviside function. H of t is equal to 0 if t is negative, and 1 if t is greater than or equal to 0. And now if we draw this thing, we'll say here's 1. We know we're 0 for every value to the left of 0, and we're 1 for every value to the right. So now, as we approach, in this case, we're going to talk about the limit as t approaches 0 of h of t. And this is something you're going to see me do constantly throughout the class. I'm going to switch from a capital letter to a lowercase letter. When we get to chapter 4, and definitely when we get to chapter 5, I will suddenly stop, because then it will matter. This is kind of sloppy on my part. I should use a capital and a capital, or a lowercase and a lowercase. These are the same h. What I'm really going to do to mess with you guys, not intentionally, but I'm going to do it, is I'm going to also jump from script to print. You might see B, you might see B, you might see B, and you might see B. And I will pretty much jump between those four at random at times. I'm sorry. I would encourage you to ask questions in the middle of lecture if you could. shoot me an email if something doesn't make sense so I can send an announcement to the class, please. This function, h of t, the Heaviside function. So if you notice, if we approach 0 from the left, well, all these points have a y value of 0. But if we approach t equals 0 from the right, all these values are 1. And in fact, we can talk about these one-sided limits. We can say, well, what's the limit? What is the pattern in the y values of h of t as we let t go to 0 from the left? As we let t go to 0 from the left. That's what that little minus sign means. So, from the left. Okay, here's the left-hand side of our paper. As we're letting t, and this is our t-axis, as we're letting t get closer and closer to 0, we can say here's -2, -1, -1 half, -0.1. As we're letting t get closer and closer to 0, well, the y values, h of t, is always 0. This pattern, as we let t go to 0 from the left, is that the y values are constantly 0. It doesn't matter that we jump up to 1, because remember, it doesn't actually matter what happens at this point. It happens as we approach that point. So the limit of h of t, as we let t go to 0 from the left, is equal to 0. But the limit of h of t, or the pattern in the y values of h of t, as we let t approach 0 from the right, as we let t approach or go to 0 from the right, is equal to 1. Because at this point, we've got a y-coordinate of 1. At this point, we've got a y-coordinate of 1, and at this point, a y-coordinate of 1, and at this point, a y-coordinate of 1. As we approach from the right, the pattern in our y values tends towards 1. But as we approach from the left, the values in our y value, the values of our y value tended towards 0. So, we can have limits from the left, and we can have limits from the right. From the left, your values are increasing to a point, and from the right, your values are decreasing to a point. Yeah, the book then goes on to a definition of a one-sided limit. We write the limit as x goes to a from the minus. I write these for me, so we would write the limit as x goes to a, we can have from the minus of f of x, or we can talk about the limit as x approaches a from the right of f of x. And both of those can equal some value L. The important thing is, and I pretended that was a theorem. So let's say we had some function. Let's go back to the first example, actually. That one in the intro. So here's our numbers. This is for f of x is equal to x squared minus x plus 2. And now, if we were to take a look at this thing, as the limit, as x approaches 2 from the left. Well, if x is approaching 2 from the left, that means x is always less than 2. That means we're talking about this column. We were steady approaching 4. And I need a f of x there. Similarly, the limit as x was approaching 2 from the right of f of x was also equal to 4. We need both of these conditions, and this is why I call what I'm about to say a theorem. This is a big takeaway from this lecture I want you guys to get. That the limit, that says lift, the limit of some function as x approaches a is equal to L. So the limit of some function as x approaches to a is equal to L if and only if. Teachers will often write IFF, if and only if. You might also see an arrow going both directions. All three of these mean the same thing. So the limit of a function as x approaches a is equal to L if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, which is equal to L. Okay, so we can say this function has this limit if the function approaches that value from the left and from the right. We have that over here. We're approaching x is equal to 2 from the left, and our y values tend towards 4. Over here, we're approaching x is equal to 2 from the right, and our y values tend towards 4. Since we approached 2 from both directions, and our y values approached the same number, that's why we were able to say that the limit of this function as x approached 2 was 4. Now, if we jump back to the heaviside limit, over here, the limit as t approached 0 from the left was equal to 0, and the limit as we let t approach 0 from the right was equal to 1. So, the limit as t approaches 0 of h of t does not exist. The y values don't approach the same value from both directions. We need them to approach the same value from both directions in order for the function to limit to that value. So be aware that we can have a left side limit equal a value and a right side limit equal a value and have the function as a whole not have a limit. Cool, so let's do another example, example 6. After a semester of doing this, it just occurred to me I could zoom my camera in and give you guys a better look at what I'm pointing at. So, this theorem is important, like I said. This thing is important, and we're going to see pictures of it here. I want to make sure I'm not tilting this thing too bad for you. There we go. Now I won't move it. So we have this function. This function is what I guess I called g of x, though I never labeled it. And we want to evaluate these limits based off of the graph of the function of g of x. So we'll do letter A first. Seems like a natural spot to start. So the limit as x approaches 2 from the left of g of x. Okay, so here is x equals 2. And as we're letting x approach 2 from the left. So from the left, these are our y values. As we get closer and closer to x is equal to 2, our y values are getting closer and closer to 3. So from the left, I should say the limit as x approaches 2 from the left of g of x is going to be equal to 3. But as we approach x from the right, now we're coming at it from the other direction, our values in x are getting closer and closer to 2, and our values in y are getting closer and closer to 1. So from the right, that limit is equal to 1. Now we've got a limit as x just approaches 2. Well, the limit from the left does not agree with the limit from the right. That means this limit does not exist. You need the limit from the left to equal the limit from the right in order for the limit to exist. Okay, so let's jump over here. Here's our line x is equal to 5. Well, as we are letting x get close to 5 from the left, our values in y, they go up and then they start to go down and they tend towards 2. Similarly, from the right, as we let x get closer and closer to 5 from the right, our y values get closer and closer to 2. And now, what's the limit as we approach 5? Well, the limit from the left is equal to 2, and the limit from the right is equal to 2. That means this limit as a whole is equal to 2. It doesn't matter if you look right here, that g of 5 is totally equal to 1. The limit, and I hope I didn't get excited and suddenly write half of that off camera. It doesn't matter that the function's value when x is equal to 5 is 1. The trend in the pattern, what the y values are tending towards, is 2 as we let x get close to 5. So you need the limit from left to equal the limit from the right, or else the limit doesn't exist. And once again, it doesn't matter the value of the function at the point x is equal to 5. We only care about what happens as we get closer and closer to 5. Cool, so let's shift gears a little bit. Let's talk about infinite limits. So, let's start off with an example. Let's find the limit as x approaches 0 of 1 over x squared. This one we can do by hand. Normally all of calculus I would do by hand, but this one let's do by hand. So we're going to create a table of values. And notice how we're going to square x. So it doesn't matter if we choose a positive or a negative value. By that I mean if we call f of x 1 over x squared, then that means let's have an x and an f of x column. If we plug in plus or minus 1, well, we're going to get plus or minus 1 out. If we plug in plus or minus 1/10, well, if we square 1/10, that gets us 1/100th, and 1 over 100th is equal to 100. If we plug in plus or minus 1/100th, well, we would square it, and that would give us 1 over 10,000, which would give us 10,000. Let me make sure that'd be a 1 with 4 zeros. Yep, 10,000. And then the last one, if we plug in plus or minus 1,000, we would get a 1 with 6 zeros, or 1,000,000. Notice how we're getting closer and closer to 0. Plus or minus 1 over a 10,000th. Now we're going to have a 1 with 8 zeros. And some commas. 100 million. So as this number gets closer and closer to 0, this number is skyrocketing. It is shooting up and up and up. And in fact, this number tends towards positive infinity. We can grow this number to be as big as we want to. If we want to, say, get 1 times 10 to the 26, we just need to plug in 1 times 10 to the 13th, or 1 over 1 times 10 to the 13th, and that'll give us that number. If we want to make this number bigger, we have to make that number smaller. But as big as we want this number to get, we can always come up with a small number that'll get us there. So the pattern in these y values increases without bounds. It tends towards positive infinity. Yeah, it tends towards positive infinity. I don't have a graph handy on my laptop, but first off, I would strongly encourage you guys to play around with some online graphing calculator. Desmos is cool. Wolfram Alpha. Shameless plug to Wolfram Alpha. It's the one of only 2 apps I have ever purchased for my phone. Wolfram Alpha is wonderful. I strongly recommend Wolfram Alpha to not just the app, but the actual website. You can go there. I strongly recommend this website to any student going through calculus. It'll help you with, not all of these words will make sense right now, but they'll help you with limits, derivatives, and integrals. This website is pretty good at checking your work. So Wolfram Alpha, they also graph things. Apparently this class is going to unofficially be brought to you by Desmos. Either of these online resources are useful in graphing, but this thing goes up like that. So, infinite limits, numbers can tend towards infinity. And what happens if we took the limit as x went to 0 of negative 1 over x squared? Well, same thing's going to happen, but in the negative direction. This thing is going to tend towards negative infinity. The use of an equal sign here, the book uses it. Infinity isn't a number. Positive infinity, negative infinity, they're not numbers. One could argue that they're concepts at best. Usually we've been saying limits are equal to a number, but remember, we're talking about patterns. We're saying that by saying this is equal to negative infinity, or by saying that this is equal to positive, and I guess I never wrote that anywhere, I'm sorry, equals positive infinity. Now I have something to point at. By saying that these limits are equal to infinity or equal to negative infinity, I'm not saying that at any point they take on these values. I'm just saying that as x is getting closer to 0 from both directions, the y values are going to increase without bound, or decrease without bound. It's that without bound part that's actually kind of important. So 1 over x squared behaves nicely, and that's why it was chosen for the first example. Something that doesn't behave as nicely is simply the limit as x approaches 0 of 1 over x. Table of values fairly straightforward. We can have an x, and I'm going to call this thing f of x again. 1, 10, 100. I'm sorry, we went the wrong direction. 0.1, 0.01, 0.001, 0.0001. That gives us a 10, 100, 1,000, 10,000 respectively. So once again, as we're getting closer and closer to 0, we're tending towards positive infinity. But now we're not squaring x. That means we're going to get different values out if we put in a negative 0.1 or a negative 0.01 or a negative 0.001. We're going to get a negative 10, negative 100, negative 1,000, negative 10,000. So, this is going to be an example of a limit that does not exist. This limit doesn't exist because as we take a look at the overall trend of 1 over x, as we let x go to 0 from the left, well, as we're getting closer, as we're getting closer to 0 from the left, all of our numbers are going to be smaller than 0. If all of our numbers are smaller than 0, that means they're going to be negative, and the closer we get to 0, the bigger in the negative direction these numbers go. One could argue their smaller a better way of saying that is they are increasing in magnitude in a negative direction. But from the left, this function approaches negative infinity. And in fact, that's when the other notation, we can say 1 over x approaches negative infinity as x approaches 0 from the left. Similarly, 1 over x approaches positive infinity as x approaches 0 from the right. But because the limit, as x goes out to 0 from the left of 1 over x, did not equal the limit as x goes to 0 from the right of 1 over x, because of this, we know that this limit does not exist. Let's draw a picture of this. In fact, this is what 1 over x looks like. It has a vertical asymptote. This is where I missed my expo markers because that would be in a different color. We have a vertical asymptote at x is equal to 0. Let's continue with that idea. Let's also find a loose piece of paper. We have this vertical asymptote, and do I care what's on the back? Yes. At x is equal to 0. Because we tend towards that infinity, we can't ever plug in what happens at x is equal to 0. But we know that as we keep on going that way, our y values keep on going that way. These limits towards infinity, limits towards, that looked bad. I think it's T-O-W-A-R-D-S. Two wards. Limits towards infinity, plus or minus infinity. This idea is the same thing as vertical asymptotes. Now we can just use the tools of calculus to show that a vertical asymptote exists. So, you can say, let's talk about how could we, using calculus, show that f of x is equal to 1 over x minus 2 has a vertical asymptote at x equals 2. So the book goes through, calls this thing a definition. It's kind of like a theorem. So the book says the vertical line x is equal to a is called a vertical asymptote if this curve has at least one of the following statements. Solid. So this is a very calculus way describing it. We have a vertical asymptote if these things go like that, if we have a graph that looks like that, if we have a graph that looks like that, or if we have a graph that looks like that. Hopefully you guys have seen graphs of vertical asymptotes before. And hopefully we're taking something you know something about, vertical asymptotes. And I should probably draw my dashed lines. That's why they pay me the big bucks. Vertical asymptote, something you guys hopefully know some things about. Now we're using calculus to prove that they exist. Well, using calculus showed that that function has a vertical asymptote there. All we have to do is we have to take a limit as x. We're going to have to go from different directions as x approaches 2 from the left of 1 over x minus 2. Well, as we approach 2 from the left, and I'm going to draw a little number line to help illustrate this. Here's 2. To the left of 2, we got 1.5, we've got 1.75, we've got 1.9. Over here to the left, all of our numbers are smaller than 2. They're left on a number line. So, if no matter what number that's over here, When I take 2 away from it, it's going to be a negative number. This numerator is always positive. This denominator, for the sake of this limit, is always going to be negative. And this denominator is getting incredibly small. That's something over here that I didn't necessarily say, and I want to again. Looking at the top, 1 over 0.1, 1 over 0.01, 1 over 0.001. These denominators are getting smaller and smaller, but the number as a whole is getting bigger and bigger. Well, this denominator is going to get incredibly small if we let x get incredibly close to 2. That means this number as a whole is going to get incredibly large. Since we're always going to be negative, that means we're going to tend towards negative infinity. Similarly, and this is enough to show that a vertical asymptote exists. Similarly, we could say that the limit as x approaches 2 from the right of 1 over x minus 2. Well, now we're over here from the right. We've got numbers like 2.1, 2.5, 3, 17's way out there. When we take 2 away from it, these numbers are always going to be positive. They're going to get really small, but they're always going to be positive. So this thing is going to tend towards positive infinity. Sorry, I keep on checking my camera. I have recorded lectures without hitting record before. That was not a fun day. So, a big takeaway, if the denominator shrinks and the numerator stays the same, the numbers get bigger. So, using calc to show that a vertical asymptote exists, just take the limit at that point. Or take the limit as we approach it from different directions. Because notice how the limit isn't going to exist. The limit, as x just approaches 2 of 1 over x minus 2, does not exist. That is not enough to show that a vertical asymptote exists. I'll say that again because I think I kind of messed that up. This is not enough, knowing that this limit does not exist, is not enough to show that a vertical asymptote exists. Let me grab another piece of paper. So, we could have some function that goes like that. Now clearly the limit from the left does not match the limit from the right. That means this limit does not exist. However, we do not have a vertical asymptote. What we need one of the 6 conditions. We need either the limit as x approaches a from the left of some function to equal positive infinity. That's something that looks, as we approach from the left, it goes up towards positive infinity. Doesn't matter what happens on this side. We could have something that looks like that. That's fine. We could have something that goes, yeah, this is fine. As we approach a from the left, we go off to positive infinity. That lets you know there's a vertical asymptote at x is equal to a. We could have a limit as x goes off to a from the right of f of x. That could equal infinity. And we could have something that looks like that. We would still get our vertical asymptote because these values are going to increase without bound. Or we can have a limit as x just plain old approaches a of f of x going to infinity. And that would be something that looks like this. Now I believe I said that we had 6 things to worry about. Well, our 6 things arise from if I put a minus sign out in front over here, we would have a function that looks like that. And we would still get our vertical asymptote. If I put a minus sign here, we would get a function that looks like that. Now we're just going towards negative infinity. If I put a minus sign here, we get a function that looks like that, going towards negative infinity. So we need a limit going to infinity, not necessarily not existing, because the limit doesn't exist, but we don't have a vertical asymptote. We need something to go to either positive infinity or negative infinity to know a vertical asymptote exists. Okay, so I feel like this lecture is getting a little long, so I want to cover really 2, maybe 3 more examples real quick, and then I'll let you guys, set you guys free. You can pause the video and walk away whenever you like. So, if we were told to find the limit as x goes to 3 from the right of 2x over x minus 3. If we were told to find the limit, you would point at it and you'd be done. No, students often ask, how do you show work for these problems? A lot of these problems, especially as we progress through this class, this has very little work to show. You could create a table of values, and that is arguably the best way to show. But what you can do is you could say that, x minus 3 approaches 0 as x approaches 3 from the right. That tells you, so that thing is going to 0, x is going to 3 from the right, so the denominator is always going to be positive, but getting really small. That tells you that the limit as x approaches 3 from the right of 2x over x minus 3 tends towards positive infinity. If you wanted to say find the limit as x approaches 2 from the left, we'll say x squared minus 1 all over x minus 2. Okay, so once again, x minus 2 goes to 0 as x goes to 2 from the left. Now, we're going to 2 from the left. When we're really close to 2, x squared minus 1 is always positive. It doesn't matter if we're on to the left of 2 or to the right of 2. When we're really close to 2, that thing's really close to 4, and we're going to take 1 away from it. So that numerator is really close to 3. The important thing is that numerator is always going to be positive. Now, over here, we're going to be approaching 2, but we're going to be coming at it from the left. All of our values of x are going to be smaller than 2 because we're coming at it from the left, but we are approaching 2. That means this denominator is going to approach x minus 2 goes to 0 yeah, I had that right, sorry. X goes to 2 from the left. Cool. So yeah, numerator's positive, numerator's always 3, denominator is getting really close to 0, but since we're always plugging in numbers that are less than 2, this denominator is always going to be negative, and a positive divided by a negative is going to yield a negative number. So we'd say this limit is equal to a negative infinity. Don't really need to make a table of values. Here in a couple sections, you'll be able to just say infinity and be done with it. In these first couple sections, we're still trying to develop skills, trying to get you guys thinking of things formally. That's why we're going through all this. 2 more examples and a fun fact for you. So, I know that, so I warn you guys that trigonometry is a prerequisite for this course. If it's been a while since you guys have taken trigonometry, I would suggest you guys go over your unit circle real quick. Calculus is done in radians, not in degrees. if you guys go on and be engineers, a lot of your formulas might get converted over to degrees, but calculus as a mathematical discipline gets done in radians. So if we wanted to find I and D, the vertical asymptotes for y equals the tan of x, so where do all of the vertical asymptotes for y is equal to the tangent of x occur? Well, y, which is the tangent of x, remember that tangent of x is the same as the sine of x divided by the cosine of x. We know that we're going to have a vertical asymptote when the cosine of x is equal to 0. Whenever the denominator goes to 0, you're going to have, whenever the denominator goes to 0, I can't say that. I can say that when the denominator goes to 0 at a different rate, but we don't yet have the tools needed to discuss rates. Whenever a function is in lowest forms, is most reduced. So what do I mean by that? That means, you know how x squared minus 1 divided by x plus 1 can become, if you factor the numerator and cancel out x minus 1? If you can't reduce that thing anymore, wherever the denominator equals 0, you have a vertical asymptote. This thing we could simplify, so that's why we didn't have a vertical asymptote over there. This does not simplify any further, so whenever cosine is equal to 0, we know that tangent is going to have a vertical asymptote. Well, say you forgot trigonometry, which is fine. I don't know the last time you guys were in a math class. And I know that you can test into calculus without ever taking a trigonometry course, yet why it's required but you can get around it is beyond me. Points on your unit circle are in the form cosine of theta, sine of theta. So when cosine is equal to 0, that means, well, that's when your x-coordinate has to be equal to 0. That happens when theta is equal to pi halves, or when theta is equal to 3 pi halves, or we can go all the way around to get back to 5 pi halves, or if we went in the opposite direction, we'd have it at negative pi halves. So we know that the cosine of theta is equal to 0, or cosine of x is equal to 0, when x is equal to pi halves plus some integer n times pi. So we know that the limit as x approaches pi halves plus n pi of the tangent of x, that one's not going to exist because of the way tangent looks. It wiggles. But we know whenever we approach these values from the left, we're going to go to a positive infinity, or whenever we approach these values from the right, we're going to go to a negative infinity. So, finding vertical asymptotes is really finding where denominators equal to 0 after you have completely reduced your function. So final example, this is going to be our example 10. You guys are going to have a couple problems in your homework like this. So what we want to do is, I'll stick that there and let me make sure that everything is lined up just right. So we want to sketch an example function that satisfies these 6 conditions. And you'll have to excuse me, I just realized that my camera is about dead. And one of my cats is making a guest appearance. This is Hooper. Sophie's nearby. So, we want the limit of this function to equal, or to tend towards infinity when we go to 2 from the right. We want the limit of the function to not exist at 2 And that's all that we have for 2. So let's draw. Ooh, that was a bad. That's killing trees. Let's try that again. We don't need those. So here's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Fine. So as we approach 2 from the right, so here's x is equal to 2, we're going to go to positive infinity. That tells us we have this vertical asymptote at x is equal to 2. And we're going to tend towards it as x approaches 2 from the right. So we'll look something like that. However, the limit as x approaches 2 does not exist. Okay, so that means the limit from the left can't be equal to positive infinity. So that means the limit from the left could equal anything that isn't positive infinity. We'll have it be negative infinity. That's fine. So that takes care of that one. We know we've got some information here about negative 1. We know that f of negative 1 is equal to negative 2. But we know that the limit as we approach negative 1 is positive 3. So that means we could snake up to positive 3. Okay, that takes care of that one. We know that f of negative 3 is equal to a positive 4. So that's way up here. So let's continue our limit. Oops, not that one. Is equal to 4, but we know that the limit as we approach negative 4 is going to be negative infinity. There we go. So this is one possible graph that satisfies these 6 conditions. We go up, we kind of snake around. We don't have that part. One possible graph. We could do another one. I'm going to flip this thing over. Oh, so once again, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So as x approaches 2 from the right, we're going to go to positive infinity. So let's start way down here. And then as x approaches 2, that limit doesn't exist. So now we're going to say that this totally works. Okay, so we know that f of negative 1 is equal to negative 2. There's nothing we can do about that. And f of negative 3 is equal to positive 4. There's nothing we can do about that. Negative 2 and positive 4. Now we just have 2 more limits. So as we approach negative 4 from the left, we go to negative infinity. So we'll have something that looks like that. That takes care of... Sorry, my camera died, but the function will go down here and hit this value. So you can draw different the limit as we went to 2 from the right, went up to positive infinity. Oops, so we have to jump back up here. Sorry about that. My camera just died. You can generate different graphs based off of this information alone. There's a lot of this graph that you don't have information for. You're going to be asked to do 2 of these on your homework. Note that you get different, mathematicians would say this, there are infinitely many solutions for problems like this. So don't get discouraged if your solution doesn't look like someone in your classes. there are infinitely many different graphs you can draw from this information. Go off and do this homework. It's already up on Blackboard. 1, 5 through 9 odd, 15, 17, 31 through 43 odd. And send me an email if you guys have any questions. If it's a Tuesday or a Thursday, a text is probably the best way to get a hold of me. Monday, Wednesday, Friday, anytime on the weekend, anytime whenever you guys can try and get a hold of me. I'm here to help you. Good luck, everybody. This assignment and the other assignment, 2.1, they are going to be due in my inbox by 9 p.m. on Friday. Yeah, take it easy, everyone. Bye-bye.